You know, there's a specific feeling every engineer has had. It's maybe 3:00 a.m. You're staring at a dashboard, your eyes are just burning, the system is crawling, or it's completely down. And the logs?
The logs are clean.
The logs are clean, green lights everywhere, the code hasn't changed, the config is identical. But something is definitely broken.
Ah, yes. The ghost in the machine.
Exactly. And, you know, ideally, we call that a bug. We find a line of code, we fix it, we go to sleep.
Right.
But more and more, it just feels like a mystery. And today we are doing a deep dive into a stack of documents that claims those mysteries.
Well, they aren't actually mysteries. They're just a layer of reality we've chosen to ignore.
And to be honest, a layer we really can't afford to ignore anymore.
We are looking at the XR series architecture by Dennis T.Y. Leo, and the headline claim here is, it's massive.
Yeah.
It's not make servers faster.
Yo.
It's architecting the reliability fabric of civilization.
It sounds hyperbolic, doesn't it? Like almost sci-fi.
It really does. But when you actually dig into the source material, the GitHub docs, the lecture transcripts, it's grounded in this very gritty, very uncomfortable reality. It's not about writing better code. It's about the fact that the physical world is messy and kind of rude, and our digital systems are all pretending it isn't.
That's the core tension right there.
Yeah.
We have this stack, and the central argument is that the way we build technology today is, well, it's fundamentally disconnected from physics.
Totally.
We assume that if a server crashes, someone made a mistake, a typo, a loose wire, you know, cause and effect.
Right, that Newtonian view. You push the button works. If it doesn't, well, the button's broken. But Leo's argument is that modern infrastructure, cloud computing, AI grids, these massive systems, they don't fail because of errors in that old sense. They fail because of silent drift.
Okay, let's nail this term down right away. Silent drift. It sounds like a horror movie villain. What exactly are we talking about here?
So in the document, silent drift is defined as the accumulation of all these invisible physical variations.
Yeah.
We are talking about a line of bad code that always fails. We're talking about like margin decay, thermal instability, jitter accumulation.
Okay, but for, you know, the non-hardware engineers listening, give us a concrete example. What does that drift actually look like in the wild?
Think about an SSD,
Got it.
a solid-state drive. In the software world, you write a file. It saves. It's binary, yes or no. But in the physical world, that drive has what's called tail latency. So maybe it's usually super fast, but once every million operations, it hangs for, say, 50 milliseconds. And that's because of a tiny voltage fluctuation or a thermal throttle because a fan slowed down for a second.
Which on its own, who cares? 50 milliseconds is a blink.
Exactly. One drive, one time, it doesn't matter. But now imagine you have 10,000 of those drives across 3 data centers.
Right.
All running a synchronized database for a bank or a hospital. Suddenly, all those tiny invisible drifts in the latency start to stack up. They compound. And eventually, they cross a threshold the software was never built to handle. And the system just locks up. No error code, no bug, just physics.
And that's the silent part. The logs don't say, hey, physics is happening. They just say time out.
And that is the problem the XR series architecture is trying to solve. The mission statement here is pretty absolute. To detect these failures before they even exist. To govern the drift before it cascades into a catastrophe.
It's almost like precognition for servers.
It's high-resolution monitoring, but yeah, at a layer we usually just pretend doesn't exist. It's looking for the smoke before the fire even starts.
Before we get into the how, and there is a serious alphabet soup of acronyms we need to decode here, I want to talk about the why. Because the creator, Dennis Leo, his background really contextualizes this obsession with the invisible. He didn't start in, you know, comfy cloud software, did he?
No, not at all. He cut his teeth at Intertech, building automated test systems, ATS, for power supplies.
And as someone who has mostly stayed in the software lane, reading his description of power engineering was, wow, eye-opening. He says, debugging power modules is nothing like debugging digital logic.
It's a completely different universe.
Yeah.
In digital logic, you have discrete states, on or off, true or false.
Right.
In power, you have magnetic behavior, you have parasitics, which are these stray capacitances that exist just because components are physically near each other. You have EMI shadows. It's messy.
There's one specific image he used in a transcript that I just cannot get it out of my head. He's talking about trying to stabilize a waveform on a scope, and he says, sometimes just breathing on a probe changes the waveform.
Oh, it's so visceral, isn't it?
It's terrifying. You're just standing there, this biological entity, and your breath is the variable that crashes the whole system.
And it highlights the fragility of that physical layer. We love to think the cloud is this ethereal, perfect place.
The cloud.
Right. But underneath, it's silicon, copper, and electricity. And as Leo puts it in one of the transcripts, physics isn't polite.
Physics isn't polite. That feels like the bumper sticker for this entire deep dive.
It really is. He explains that in this physical layer, failures just don't repeat. You know the Heisenbug, the bug that vanishes the moment you try to observe it.
Oh yeah, every developer's nightmare. You attach the debugger and poof, the app works fine. You take it off, it crashes.
In his world, that's just Tuesday. You might stress test a power unit for 3 days, catch one tiny glitch, and then realize you can't reproduce it because the root cause was a specific atmospheric pressure interacting with a specific thermal load. You can't simulate that.
And this leads to what I think is the most validating point for any burnt-out engineer listening. He argues that the problem isn't that we're not smart enough, it's that we literally don't have the time.
Right. He says the world didn't outgrow you. The world outgrew the time window humans are given to debug.
That is such a crucial distinction. The complexity of these interactions, the drift, the jitter, all of it, it happens faster and more subtly than a human brain can possibly track.
Not in an 8-hour day, not even in a 24-hour day. If a thermal drift only triggers a failure once every 3 weeks under a full moon, you are never going to catch that by staring at logs.
Right.
You need a different approach.
So if we accept that humans are too slow and physics is too rude, what's the solution? This is where the source material introduces the concept of embedding.
Now, usually when we hear embedding, we think of like vector databases and AI, but he's talking about something different. He's talking about embedding observability into the hardware itself.
He calls it the whisper. I love that phrasing.
It's poetic, but it's also very technical. So think about how a modern cloud server runs. You've got a scheduler shifting workloads across UMA nodes.
Pause on UMA nodes for a second.
Oh, right. Non-uniform memory access.
So some memory is closer to the processor.
Exactly. Accessing the far memory takes longer. So the scheduler moves work around, memory residency drifts, the kernel adjusts frequency governors to save power.
It's a constant dance inside the machine.
It is. And in that dance, there are these tiny signals, a flood of netlink messages, a transition in the sys file system. Individually, they're totally benign. But Leo argues that if you look at them all together, they whisper. They whisper that the system's intent and its actual behavior are drifting apart.
And if you ignore the whisper,
you get what he calls 1119, which is a reference to a major outage pattern. You get the cascade.
Okay, so that's the problem statement. We've got silent drift, we've got whispers of failure, and humans who are too slow to hear them. Enter the XR series architecture.
The solution.
And the philosophy here starts with a really simple rule. Core before shell.
This is such a direct shot at modern software development. We love abstractions, we love wrapping things in containers, then orchestrators, then dashboards. We build these beautiful shells to hide all the messy complexity underneath.
Abstracted away is the mantra of the last decade, right? If you can't see the mess, it doesn't exist.
And Leo just says, stop. No empty shells. You cannot build a reliable system if the core component doesn't know what's happening to it physically. If you put a fancy dashboard on a server that doesn't know its own thermal drift, you're just decorating a ticking time bomb.
This leads into probably the most complex concept in the documents, but I think it's the pivot for the whole theory. Reliability as a vector economy.
Yeah, this took me a minute to wrap my head around too. Usually reliability is, a binary score, pass-fail. Or maybe a percentage like 5 nines, 99.999% uptime.
Right. Is it up? Yes. Is it down?
No. But Leo wants to turn reliability into math. He wants to take those abstract forces, the margin loss, the drift, the jitter, and convert them into causal vectors.
And vectors imply direction and magnitude. So it's not just bad, it's bad in this specific direction by this much.
Exactly. Instead of saying my server feels sluggish, you have a vector that says thermal margin has decreased by 4% while interrupt latency has increased by 2%. Now you have numbers. And if you have numbers, you have an economy.
You can trade it. You can value it.
You can optimize it mathematically. It transforms reliability from just a vibe into a tangible asset.
But to do that, you need tools. And this is where the XR series gets really specific. There are, 5 or 6 core components here that form this unified reliability architecture?
Yep.
Let's break them down, starting with the detective, XRAD.
The Extreme Reliability AI Debugger.
Now, AI debugger
Ah.
immediately sounds like marketing fluff. You know, everyone slaps AI on everything now. How does this actually work?
So XRD is bottom up. Most debuggers sit at the OS level, right? They
Yeah.
read logs.
Right.
XRD reconstructs those causal vectors we just talked about, but from the silicon layer up, it's looking at thermal deltas, power fluctuations, firmware version changes.
So it's not reading the error message, it's reading the physical environment that created the error in the first place.
It connects the physics to the failure. Instead of telling you the database crashed, it tells you thermal instability in core 4 caused a firmware timing miss, which then caused the database to crash.
Wow. That is a massive difference in resolution. It's like the difference between saying the car stopped and the fuel injector clogged because of bad gas.
Precisely. But for XRAD to work, it needs data. And that data comes from XSM, the signal fabric tap layer.
The nervous system.
Yes, that's a great way to put it. XSM is what captures the physical layer truth. It is the component that would notice if someone breathed on the probe. It detects jitter, timing margins, signal integrity. It's listening for the whisper constantly.
Okay, so XSM feels the pain, XRAD figures out what caused it. Then we have XENOS, the causal boundary governor.
This one is my favorite because it addresses organizational chaos just as much as technical chaos.
It's the stay in your lane protocol.
Totally. One of the biggest reasons complex systems fail is responsibility drift. The hardware team says it's a firmware issue. Firmware says it's the OS. The OS team blames the app.
And while they're all arguing, the site is down. Oh, I've been in those meetings. It's 3 hours of just finger pointing.
XENOS enforces boundary integrity. It basically says, no, this issue originated here in the silicon. It is not allowed to propagate up and crash the application. It isolates the fault at the layer it actually occurred.
That seems incredibly difficult to enforce, though.
It is. It requires the hardware to be smart enough to trap its own errors before they bubble up.
Yeah.
And that's why core before shell is so important. You can't have a dumb core and a smart shell. XENOS demands a smart core.
Then we have the bridge to us, to the human user, XAPS, the semantic engine.
Right, because even with all these amazing vectors, a human operator eventually has to make a decision. XAPS translates the video is lagging into there's a congestion vector in switch 4. It maps the human complaint to the machine's reality.
And tying it all together is the XRBUS.
The causal interconnect fabric. It's really just the standard language, the protocol that lets XRAD, XSM, and XENOS talk to each other without losing any data in translation.
It's a formidable stack. I mean, if you actually built this, a system that can feel physics, debug it, police it, and explain it, you'd have something incredibly robust. But the documents don't stop at the engineering.
No.
And this is where the deep dive gets a little philosophical.
It shifts into economics, even sociology.
Because Leo acknowledges this hard truth. You can build the perfect reliability tool, but if it costs money to run and nobody wants to pay for it,
You won't get used. Exactly. Incentives. If I'm a big cloud provider, do I really want to spend millions fixing a whisper of a problem that hasn't actually caused an outage yet?
probably not. You wait for it to break, then you issue a service credit. It's cheaper.
That's the old break-fix model. And Leo introduces XRAS, the incentive engine, and XRST, the settlement tokenization engine, to break that exact cycle.
Okay, tokenization. We have to tread carefully here because the moment people hear tokens, they think crypto speculation, monkey JPEGs, scams. Is that what this is?
No, and distinction is so vital. He's not talking about a coin you buy on an exchange. He's talking about tokenizing reliability improvements. It's much closer to an insurance contract or a service level agreement, an SLA, than it is to a cryptocurrency.
Okay, walk me through how that would work in practice.
So imagine an OEM, a manufacturer, delivers a new server rack. Usually they sell it and they walk away. Maybe there's a warranty. But with XRST, if that manufacturer can prove, using these vectors, that their hardware is running drift-free, that they're effectively managing the physical chaos, that proof gets tokenized.
It becomes a settled asset, a record of truth.
Right. The operator pays for that proven reliability. And if the system drifts and fails, the manufacturer loses tokens, it aligns the incentives. Suddenly finding that invisible bug isn't just good engineering that costs you time, it's actually revenue.
It gamifies stability.
It creates a market for it. Verifiable risk transfer. Today, when a major cloud goes down, it's a huge mess of lawyers and credits. Leo is proposing an automated mathematical settlement based on the actual physics of the failure.
That completely changes reliability from a cost center, I have to pay to fix this, to a value center, I get paid if this stays stable.
Which is the only way you solve this problem at the scale of civilization. You can't rely on goodwill. You can't just hope the engineers are doing their best. You need an economic engine that actually rewards them for it.
And this brings in the final pieces of the puzzle, XIP and XROG.
The governance layers. XIP is the integration plane. It ensures every single device from every vendor speaks this same reliability language. It's like a building code. You can't bring a brick into this skyscraper unless that brick knows how to report its own stress levels.
And XROG.
Multi-cloud governance. It's about extending that building code across different clouds. So if you run a workload on, say, Google and AWS at the same time, XROG ensures the reliability definitions match up so you don't get lost in translation.
It is incredibly comprehensive. It feels like Leo looked at the entire stack from the atom vibrating in a transistor all the way up to the legal contract signed by the CEO and said, this is all one system, and it's all broken.
Or at least it's all drifting. And because it's drifting silently, we've been lulled into this false sense of security.
So let's zoom out. We've gone from the frustration of an engineer literally breathing on a probe all the way to a global economic architecture for reliability. What is the big takeaway here? When you close these documents, what's the thing that stays with you?
For me, it's the realization that we are moving from an era of repair to an era of governance.
Repair versus governance. That's a strong distinction.
Think about the last 30 years of tech. Move fast and break things. That was the motto.
Yeah.
And it worked great for social media apps. It does not work for the fabric of civilization.
You can't move fast and break things with a placemaker, or a power grid, or the AI running the stock market.
Exactly. When the stakes get that high, fixing it when it breaks is just negligence. The XR series suggests we need to govern the invisible drift. We have to align the economics of the system with the physics of the machine.
It's a fundamental acknowledgement that code doesn't exist in a vacuum. It lives on physical stuff that gets hot, that degrades, that has parasitics. And if we ignore that physical reality, the digital world will eventually crumble.
And the provocative thought at the very end of the source material, the idea that reliability is the hidden architecture, that really stuck with me.
How so?
Well, if we can truly tokenize reliability, if we can trade it and track it and even hoard it using something like XRST, does that mean reliability itself becomes a new form of capital?
Reliability as a currency.
Think about the world right now. It's chaotic. Entropy is always increasing. In a world of constant disruption, maybe the most valuable thing you can possess is the certainty that your system won't fail.
That certainty might be the new gold standard of the 21st century.
And the ability to prove it mathematically, that's real power. And that's what this architecture is ultimately promising.
That is a heavy thought. We usually value speed or storage or processing power, but maybe the ultimate luxury is just stability.
Stability is the platform everything else is built on. If that crumbles, the speed doesn't matter one bit.
Well, on that note, I'm gonna go look at my laptop very, very suspiciously. I'm wondering what silent drifts are happening in there right now.
You gotta listen for the whisper.
Listen for the whisper before it becomes a scream. Thanks for guiding us through this dense architecture. It's rare we get to look under the hood of the entire industry like this.
My pleasure.
And to you listening, thanks for diving deep with us. We'll see you in the next one.